yeah, I'm going to talk about Monte Carlo algorithms, which has been one of my main interests for my entire research career. And so I'm going to call this the magic of Monte Carlo. And I'll start by trying to explain Monte Carlo algorithms as I think about them. And I come from statistics, and I know a lot of you come from engineering. And so hopefully we'll be able to understand each other okay. And and then I'll start by explaining them in general, and then I'll try to talk about some of the research questions I like to think about. To start off, so you could say, what is Monte Carlo? Well, there's different answers one could give. One is, this is Monte Carlo. It's a beautiful region in the Principality of Monaco, just attached to France and by the Mediterranean Sea, and a lot of rich people live there, and they have nice big boats and everything. And some very clever Monte Carlo researcher realized it would be a nice place to hold a conference. And so we had a Monte Carlo conference, and this is a bit of a small screen, you might not be able to see too well, but this is the Casino Monte Carlo, the famous casino at Monte Carlo. And this is a bunch of strange-looking statisticians. One of them is this tall, hairy guy here. That's me. So then they said we should invent other algorithms, like maybe the Bora Bora algorithm, and then we could have a conference there, but we haven't done that yet. But anyway, okay, so I'm not going to talk about Monte Carlo the place. I'm going to talk about Monte Carlo algorithms. So probably, I'm guessing, a lot of you, if not all of you, have heard something about and maybe make use of and have your own ideas related to Monte Carlo algorithms. I'll try to talk about how I think about them. So if I had to summarize Monte Carlo in one little phrase, I might say, to sample is to know. And what do I mean by that? I mean sort of that somehow if we can write computer programs that sample from big complicated distributions describing complicated things, sample with the right probabilities, then maybe we can learn all about them. And so it's a bit of a simplistic way to start off, but it's an extremely popular method, as again, I'm sure most of you know, and it's widely used in all sorts of subjects. So I sort of come from the Bayesian statistics community, where we often have a posterior distribution, and we want to be able to understand and sample from that. But it has applications in all sorts of things, from medicine and genetics and physics and chemistry and finance and insurance and so on. And it has a lot of applications in engineering, as a lot of you will know pretty well. And so what do I mean saying it a little bit more extended? I could say, well, usually, at least the way I think about it, is we think there's some underlying probability distribution. It says, so I'm going to always write a blue pie. I'm not sure if you can see, there's a blue pie here. And that is going to be a probability distribution, or a probability density. And it's supposed to correspond to something that's high dimensional and complicated, but also really, really important. So in a Bayesian statistics problem, it might be the posterior density. And in general, whatever sort of application you're doing, so if it's a medical application, it might correspond to variables for all the different patients and what happens to their disease, and do they get better or worse, or do they take this drug, and if they do they get better and worse, and so on. I'd imagine all sorts of things in engineering, whether it's the internet packets or the reliability of a product, whatever you've got, you're going to have all sorts of different variables. So it's sort of a high-dimensional vector of all sorts of different variables. And then we think of having some probability density or probability distribution pi, which corresponds to all the probabilities. So what's the chance that this thing fails, or what's the chance that this patient dies, and also the joint probabilities. What's the chance that all these patients die, or that this one takes the medicine but this one dies, and so on. So some big high-dimensional probability density. What it is depends a lot on the application, but from my perspective, to some extent, or at least for today's talk, doesn't matter so much. We just say, well, we have some big complicated probability density pi, and if only we knew all about pi, then we know everything for our application, right? We know all the probabilities for things to happen. We know on average what's going to happen. We kind of know everything. But then when I say to sample is to know, what I'm saying is that if pi is a big complicated density, maybe we can't just compute the probabilities, right? In principle, we could compute probabilities by taking an integral of a density and so on, but maybe we can't. Maybe it's too complicated. But if we could sample, so suppose we could get, and again, I'm sorry, this is a little small here, but if x1, x2, up to x some number were samples from pi. So what I mean by this is, suppose we could write a computer program which would output, say, some random vectors, and each one corresponds to all the possible variables in our big complicated model. But suppose it outputted them with the right probabilities. So when I say sample, I mean something that has the right probabilities. So one time the patient lives, and the next time the patient dies, and so on. But it happens with the right probabilities. So if we could do that, then we could estimate everything about pi. So for example, a lot of people like to visualize complicated high-dimensional distributions. Well, if you could get a sample of values, you could use that to generate a histogram or a density estimate or some other way to sort of visualize the probability. But also you could estimate, for example, the mean of pi. So if we just take an average of all those, so we have all these big complicated vectors, big high dimensional vectors, each one corresponds to some possible output from our simulation. If we could average them all up, we'd end up with some average vector. And if m is large enough, we'd be saying this is, on average, this is about what happens. Or if we had some function, maybe h is our function we're trying to optimize, or h is our, our output function, and we say, well, we'd like to say what happens to h on average. No problem, compute h for all these vectors and kind of average them up. Or if you want to do a probability, you want to say, what's the chance that this patient dies? Or what's the chance that over half the patients die? Or what's the chance that the patients improve overall when they take the drug? Well, you just take an average of, say, for each vector, is it yes or no? For that vector, did the patient die or not? And if you take the fraction of times that happened, that gives you it anyway. So when I say to sample is to know, what I'm saying is if we could write a computer program to give us samples from our probabilities, then we could learn everything that we need to know. So that's kind of my starting point, and my starting point is how are we going to try to take a sample? That is, we have some complicated probabilities on some high dimensional density. How can we write a computer program that's going to sample from it? So that's kind of the starting point, and again, with applications to all different kinds of things. So then you say, well, how can we sample? And this is where things get kind of interesting. Because if you have a big, complicated, high-dimensional probability vector, which again, it's got all the variables in some big, complicated model, and then I say, fine, write me a computer program that kicks out some possible values for all the variables in your problem, but does it according to the right probabilities, how are you going to do that? It's not so clear. But one way, it turns out, it's really easy, in a sense, if you use Markov chain Monte Carlo, or MCMC, and that's kind of what I work on. And probably a lot of you have heard of MCMC or maybe worked on it before. And so the most common, what remains the most common way to do MCMC is what's called the Metropolis algorithm. And it goes back to 1953, so it was amazing. They just had very, very primitive computers, and yet they were already running the kind of algorithms I'm going to talk about. And here we are many years later, and we're still running them. And it's sort of an iterative algorithm. So I'm going to explain how it goes, and then I'm going to run a simulation to try to explain this too. But to say it in sort of symbols first, you can say, well, it's a rule for giving us vector. Remember, so x should be some high-dimensional vector corresponding to all the variables and all the probabilities. And it's going to give us a rule. And it says if we have a previous vector, it's going to give us a rule to get the next vector. And in particular, it's sort of a two-step process. First, it proposes a new state. So I'm going to call it y. And y is just proposed, just sort of a random change in x. And I'll assume that it's something symmetric about x. This will all become clear in a second. But we say, well, we've got some vector. This could be what happens to all our big complicated variables. But now let's propose a change. Maybe the variables were like this instead. And then we either accept or reject this proposal. So we look at, remember, pi was the probability density. It says how likely is it that all these things would happen. And if we try doing a tweak and we get something that's more likely, we say, yeah, it's more likely, that's good, let's accept this move. On the other hand, if we get something that's less likely, so that the probability of the new state is actually less than the old state, we say that's okay. We still might accept it. We accept it with probability given by the ratio. So the probability of this new state over the old one. So if the new one's only half as likely, we only accept it half the time. And if we don't, then we reject it and we just keep the same vector again. And then we sit back and watch the magic. So that's the title. And so let me, without further ado, get to the first of a few simulations. This is going to be the first of a few illustrations that I want to run to try to explain these Metropolis algorithm or Markov chain Monte Carlo algorithms and how they work. So what do I have here? So remember I said blue pi, which is now going to be represented by these sticks. Blue pi is supposed to correspond to a big complicated probability distribution for all these different variables, right? Well, in this case, to make it simpler to understand, there's actually only 6 possible values. So you could, if you're thinking medical, you could think the patient gets better, the patient stays the same, the patient lives, the patient dies, whatever. But some different probabilities. So we're reducing a big complicated high-dimensional thing to just 6 points. And each one of them has certain probabilities. And so the height of these blue sticks are supposed to represent the probabilities. And if you can see well enough, I mean, that's 0.1. So there's about 0.14 and 0.7 maybe and so on. It just generated randomly. And these are the probabilities that are the important ones. That if we knew these probabilities, we know everything about our situation, we'd be able to do our modeling. And yet we imagine that it's so big and complicated that we can't just compute these probabilities directly. So instead, we're going to run an algorithm. And this black dot represents our MCMC algorithm. So the way I've started it here, it's happened to start at the point 4. And then remember I said it's sort of a two-stage process. It proposes a new state, and then it either accepts it or rejects it. So the way I had it set it up for this simple illustration is it's going to propose whatever the current value is, it's going to propose to either add 1 or add 2 or subtract 1 or subtract 2 with probability a quarter each. And it's going to do it randomly, so I don't know what it's going to do. But okay, in this case, it decided to propose to move from 4 to 5. And the yellow means it's proposed, but it hasn't decided yet whether to accept or reject it. And then it's got a rule for accepting or rejecting. And remember I said that if the pi of the new state is bigger, in that case it always accepts. But in this case it's smaller, so it's going to accept this proposed move with probability given by the ratio of this over this. So in that case, looks like what, maybe 65% or something. So I'd say there's about a 65% chance it's going to accept this. I don't know, it's happening randomly, but okay, it did accept it. So that means it moves the black dot over. And that's one step of our MCMC algorithm. And then it does it again. So it's going to propose again either to add or subtract 1 or 2 with equal probability. In this case, it proposed to add 2. Now that wasn't a very good proposal because there's actually no blue stick here. So it's always going to reject that. So it's actually going to turn red, and that means we don't count that. We stay where we were. And now it's going to do it again. Okay, this time it proposed to move to 6. The stick is actually higher at 6, so it's always going to accept that. It's going to move over. And then it's going to propose, in this case 7. It's going to reject that. Let's do one more. Okay, it's going to propose to move back to 5, so it has maybe an 80% chance, because looking at the ratio of these, of accepting it. Okay, and it did. And I'm going to let it go, so it keeps doing this over and over again, where it proposes a new jump, and then it either accepts or rejects it as it goes. So it's quite a simple algorithm. And the point is, we can do these proposals just something nice and simple, like in this case, probability a quarter each, or it could be from a normal distribution or something simple. So proposing is simple. And then accepting or rejecting is simple, so we can do this on a computer, no problem. And yet, these things were actually chosen very carefully. Let me add one more thing to the simulation while it goes, and that's these black bars. And again, I hope you can see okay at the back. But so we had these blue bars, which were the heights of the target, the probabilities that we really, really wanted to understand, because they explain everything. And now we have the heights of these black bars. These just are what I could call the empirical distribution, or what fraction of the time has this black dot spent at each of these points so far. So it hasn't gotten to 1 or 2 at all yet. I guess it started at 4, so it's been to 3 a little bit, 4 and 5 a reasonable amount, and 6 the most so far. And it's again following these rules where it adds or subtracts and proposes and then either accepts or rejects. But what's the point of this? Well, the point is if we do this lots of times, then it gets more interesting. So let me speed it up a little. So it's proposing and it's add or subtracting, and then it's accepting or rejecting, and if it rejects, it stays where it is. If it proposes, it moves over, and so on. And if you follow it carefully, you can see it's still proposing and accepting and rejecting. Well, I only have an hour, so I'm going to go even faster. So here's, it's proposing and accepting and rejecting. And you can see that over time, these black bars are kind of adjusting based on what fraction of the time it's spent at each of these 6 points so far. And, well, it's not doing that great so far, but maybe you can kind of see what the point is here, that over time, what happens? Well, the black bars should converge to the blue bars. That is, the fraction of time it spends at each of these states should converge to the target probability, to the blue pi, this thing that tells us everything. So, well, why is that good news for us? Well, first of all, it can take a while, and you can see it's been going for a while. It still hasn't really gone to 4 as much as it should, and it's gone to 6 too much, and so on. I can go to a warp speed if need be, so now it's doing a warp speed calculation. And over time, the black bars should be settling down pretty well. And why is this helpful? Let me slow it down a bit. Because remember, the blue bars are standing for something that's so big and complicated and high dimensional that we can't figure out the probabilities, we can't do the integrals, we can't take the expected values. But the black dot, that's what we run on the computer, right? And that's easy to run on a computer. We just propose the new step and then we accept or reject it. Nice, simple rules. So the black dot, we can keep track of experts at MCMC, right? That's really all it is, except the only difference being that usually the blue bars wouldn't just be 6 points. They'd be a big, complicated, high-dimensional model corresponding to some big, complicated thing that you wanted to study. The point is, this is any point, is that the black bars, the empirical distribution converges to the target, or the blue bars. And so we could say sort of MCMC works. That is, it provides us with an algorithm that allows us, at least eventually, to sample from this big, complicated density. So that's kind of what it's all about. We could say it's magic, or we could say, well, this is just Markov chain theory. So as probably most of you have studied a little Markov chain theory, you know that if a Markov chain is irreducible and it's aperiodic and it has the right stationary distribution, then it should asymptotically converge to it. And that's really all that's going on here, that accept-reject probabilities were chosen exactly right to make this Markov chain actually be a reversible with respect to the target pi, if you know what that means, or in other words, have pi be a stationary distribution, so it's going to converge. So I was pretty confident, even though we were running a fresh simulation, that the black bars would eventually converge to the blue bars. So that's MCMC in a nutshell. Let me give a different example. What's the maximal distance between any two of them on average, or what's the probability that the biggest one is bigger than a certain height or something? Well, we could try to average over all possibilities, but that could be hard because there's infinite number of possibilities. We might be able to just guess, but maybe we can use Monte Carlo. So I have a region, and this is, again, just another illustrative example, but maybe a little bit more substantive one. And in this case, I have a region represented by this pink rectangle here. And I imagine for now that, say, there's 5 points which are each going to be uniformly random, equally likely to be anywhere in this region. And I say, gee, I wonder how far, say, the maximum distance, that is in this case, this point from this point is. Well, you could measure that maximum distance for this particular choice of 5 dots. But maybe there's another different choice of 5 dots. So again, it randomly put them. Wow, these are really spread apart, actually. So in this case, it's almost as far as it could be, almost from that corner up to this corner. But you say, well, we could do another one. And here's one. I guess the biggest one is from here to here. Also pretty large. It won't always be so large. That's a case where it's maybe not as large, I guess, going from here to here. And the point is, every time I resample, so in this case it's just making 5 dots uniform anywhere they want on this region, I get a different configuration from which I could measure the largest distance, or just the probability that anything is, say, to the left of this line, or anything I want to know about the arrival of these different events or these different people or whatever. And I could simulate it, right? And every time I get a new one, and I could simulate it, and I could average them up. And if I did this enough times, I get a good estimate for, on average, how far is the maximal distance between these 2 points and so on. So that's one example, a Markov chain Monte Carlo algorithm, right? Because I just said every time I get a fresh sample, I just kick up these 5 dots, no big deal. So that's kind of a little too easy for us in a way. You just kick up 5 points and do it again. But now suppose I put in a twist. Suppose I say these different dots aren't just coming uniformly and randomly any way they want. They have some interactions between them. And here's one way that I could set them up to interact with each other. And this might look a little bit ugly, this formula, but don't worry about it too much. It's just saying, suppose instead of these 5 dots being equally likely to be anywhere and they don't care about each other at all, suppose they're of the form it's often done in terms of an energy function. So the probability gets smaller when this big function h gets bigger. And what's this big function h? Well, if a and b and c, which are 3 constants here, if these are all 0, then h is just a constant, so it's just the previous case, they're uniform. But if I look at these individually, so if a is large, it's saying h is big when the distance between points is big. So in other words, it's less likely for the points to be too far apart. So suppose they tend to cluster up. They tend to get close to each other. That's what a would be telling us. B is kind of the opposite, because it's taking the reciprocal of the distances. It's saying, well, these points shouldn't get too close to each other, because if they get too close, they make a big value of h, and that makes a small probability. So if a and b are both positive, it's saying the particles shouldn't be too far, but they shouldn't be too close. It's kind of tweaking them. And then c just says, well, they shouldn't be too far to the plus x direction. So in other words, it should sort of kick them to the left. And this is a new rule for the probabilities, and because, of course, things interact with each other in all sorts of ways. And you can say, well, suppose we had this new rule. We're not just putting down 5 points any way we want. We're putting them down with these probabilities. So they're forced to not be too close and not be too far and tend to be towards the left and so on. How does that affect things like the average diameter or other things we might want to estimate? And in this case, we can't just do what we did last time of just write a program that just puts them down in the right probabilities each time, because how could I write a program that puts down 5 dots, but the probability is adjusted by this complicated formula? Not so easy, but we can use the Metropolis algorithm again. So remember, this is the thing. So far, we just put down 5 dots fresh each time, no problem. But that's because they're uniform and they don't care about each other. Suppose I want to put down 5 dots in a way that they're not too far and they're not too close and they tend to be towards left and they have all these rules based on these probabilities. Well, I'll run a Metropolis algorithm. But in this case, it looks a little different. In this case, what I'll do is each time it'll pick one of the 5 dots at random. Maybe I'll do one. Let's see, there we go. So it picked this one, and it will propose to move it again. Remember, we propose and then we accept or reject. So in this case, okay, it did a fairly timid proposal. It proposed to move it just a little bit over to there. And then it has to accept or reject in terms of whether this is a more likely or less likely configuration. Now, since this was such a timid proposal and it wasn't really any closer, I'm going to guess it's about the same probability. So it's probably going to accept it, and it did. Let's see. So again, it chose one at random. This time it chose this one. It proposed to move it again quite timidly. It's a very timid beginning here. Probably going to accept, but maybe not actually, because it's bringing it a little farther from that one. It might not be happy, but it did accept it. And I'll let it keep going. So it chooses one. It proposed to move it. Oh, it rejected that one because it was too close, actually. It doesn't want them to get too close. It accepted that one. And let me go a little further, a little faster. So it's proposing, each time choosing a random particle, proposing to move it a little bit, and then accepting or rejecting it. And again, it's probably going to accept a lot of these because they're not making such a big difference. But if they get too close, it'll probably tend to reject it. If they get too far, it'll probably tend to reject it. And also, over time, it'll tend to reject more that are moving to the right and accept more moving to the left because we know the probabilities were set up so that it should be not too close, not too far, and tend to go to the left. So let me go faster. And over time, it's selecting one, it's proposing, it's either accepting or rejecting, same as before. And over time, and I may need to speed it up a little more, but it should gradually drift to the left, and they should sort of cluster up so they're not too close and not too far. Let me go a little faster since I don't have too much time. So it's doing these proposals and accepting and rejecting. It's taking its time, but it's a little creepy. But gradually, it should be getting to the left. It's actually taking its time moving to the left because normally it'll get a little farther to the left. But you can see that they never get too close. Like they pretty much never overlap, or at least not by much. And yet they tend to get closer than they started with. They don't drift too far apart. Just as I said that, they started to drift farther apart. But and the point is, of course, we don't expect them to actually settle down because remember, we're trying to sample from a probability distribution corresponding to these interactions. So over time, we don't expect they'll ever stop moving, but we expect they'll tend to move a bit to the left. In fact, I see why they're not moving to the left. That's a bit embarrassing. Because I restarted, I had a different version which didn't have a positive value of c, so they weren't moving to the left. Another mystery solved. Let me put in a nice big value of c to make up for lost time here. And so you see with the big value of c, they actually start moving to the left, and you can see that. And for that matter, while I'm on it, let me make c negative, which just flips it around to the other side. And with a nice negative value of c, they should gradually move to the right. And remember, the proposals that I did are equally likely to propose to the right or the left. But because it's accepting more of the moves to the right and rejecting more of the moves to the left, it does that too. And you can play around with the other parameters and how much they try to be too close or too far. But you can see here, they try to go to the right, but they try to be pretty close, but not too close. So anyway, so I'll stop that one there. Okay, but anyway, so the point is whatever probabilities you want to set up, we couldn't easily write a program to exactly sample from those probabilities. But to write a program that iteratively runs a Markov chain and converges to the right probabilities, no problem. That's what we just did. So, okay, so this is MCMC, or the Metropolis algorithm, and as I say, it's so widely used because it's so easy to set up. You just do a proposal and then an accept, reject, and in principle, it can converge to any probability distribution that you want. So I could pretty much stop here because now, if you weren't before, we're all experts at MCMC and see how it can be used in all sorts of ways, but I do have to explain what I've been doing for the last 20 years as a researcher. So I've been working on research questions that are related to this, and some of them more on the theoretical or mathematical side. And what I want to do is give you a little bit of an idea of some of the things that I think about. So the first and first, just to set up graphics, I was going to say, here's sort of a typical run we could use. Maybe I'll spread out this. So here's a case where I've done sort of a trace plot. And here the target blue, instead of just being 6 dots or whatever, was actually a normal distribution given by the blue here. And as time moves up, this is showing what happened to a Markov chain. I ran a simple Markov chain on this. And you can see that it moves around, but it moves around roughly according to the right probabilities. And if we do a histogram, we say what fraction of the time did the black dot spend at each of these points. We get a histogram which nicely approximates it. So I'll use that as kind of illustrations for some of what I come back to. I think what's maybe the first question you could ask, although unfortunately one of the last questions to answer because it's a hard question, is what I'll call quantitative convergence bounds. Or one way to say it is, we sort of know, as I already said, this irreducible and aperiodic, that eventually it converges. So if you think back to that first example, it says, those black bars which say what fraction of the time we spent somewhere, those should converge to the blue bars, which are the target, the thing we really want to understand. So that's good. But I've underlined now the word eventually. That is, eventually, these black bars should converge to the blue bars. But a very natural question is, how quickly does this happen? How quickly do the black bars get close to the blue bars? Or how quickly does this Markov chain converge to the target probabilities? And if you think about it, that's a pretty important question from a practical point of view, because if you run one of these algorithms, you don't run it infinitely often, right? You run it on a computer for a while, and then you say, okay, we think we're getting some pretty good samples, and maybe you base all sorts of conclusions about your model or your medicine or your whatever based on these samples. But you say, well, have we really run it long enough that we're getting a pretty good sample? And so this is something that I've worked on a lot, and basically we'd like to prove that they're within some small tolerance, like let's say 0.01, after some specific number, say n star of iterations. And that turns out to be a hard problem, as I discovered in the first part of my research career, because I worked on these questions quite a bit. And I did make some progress, and one method I'll just say quickly is the method of coupling of Markov chains that some of you may know, where you imagine having two different copies of the Markov chain, starting in different places, but updating according to certain rules, and maybe they become more equal. And if they do, that says something about their probabilities becoming equal. And so I worked on that some, and in particular, one example was a 20-dimensional sort of application of a Bayesian posterior in a pretty complicated model. And I could prove in that case, using this model that these other people had run, these statisticians, I said I could take n star as 140. That is, I could prove if you ran their updates for 140 times, you get within 0.01 of having the right probabilities. So I was pretty proud of that. I thought that was pretty good. But I quickly learned that even though with a really large amount of work I could solve a few of these problems, it was too hard to solve them, and it wasn't going to be that widespread used, because MCMC is used in all sorts of ways and people run new algorithms. They're not going to stop to write a research paper about proving how close it gets to convergence. So whereas there's some interesting results about these quantitative convergence bounds, it hasn't really changed the way people do MCMC, because it's too hard to figure it out. But something related to it is what we sometimes call, there's lots of other theory known, and one thing is what I'll call qualitative convergence bounds. And so if quantitative convergence bounds said, give me a number such that after that many iterations, you're within 0.01 of the right distribution, qualitative convergence bounds says, well, maybe we don't know exactly how long it's going to take for this convergence to happen, but maybe we can at least talk about the sort of functional form of the convergence. And in particular, we can say, is this convergence, we know the black bars are eventually converging to the blue bars, the probabilities are eventually converging. Does it at least happen exponentially quickly? So in other words, is there some sort of rho less than 1 such that how far we are after running this for n iterations is less than a constant times rho to the n. So it's something which is decreasing sort of exponentially quickly or geometrically quickly. And that's called being geometrically ergodic. When I first heard about geometric ergodicity, I was a little skeptical. I thought, no, I'm working really hard on these quantitative bounds, because that really tells us how long we want to run it for. And they said, yeah, that's too hard. We want to work on these geometric ergodicity bounds. But eventually I decided, yeah, they're probably right. So I started working on them too. And I said, okay, well, maybe that's interesting, these geometric bounds. And it turns out that even though it's pretty hard to get the exact quantitative bounds on how quickly it converges, to just say it converges at some geometric rate, sometimes it's not too hard to say, okay, it's going to have to converge at some geometric rate. And you can say, does it really matter? As I say, I was a little skeptical, but I was eventually convinced, and it turns out it can matter a lot. And let me give one particular example. I'll call it sort of a case study. And this is a version of what's actually called the independent sampler. So it's still a version of these algorithms which propose a new iteration and then either accept or reject it. It's a little different than the sort of random walk Metropolis I told you before, but in a way that we shouldn't worry about too much. It's something called the Metropolis Hastings algorithm. And it's just a case study, which is again a very simple one, but turned out to be interesting. And it said, suppose the target, that is pi, the blue bar is the thing we really care about, suppose it's an exponential distribution. So again, sorry this is so small, but it's just saying e to the minus x. So it's a sort of one-dimensional exponential distribution, very simple common probability density. And suppose the proposals, the thing that we're going to propose and then either accept or reject, are given by an exponential with parameter k. So that is density constant times e to the minus ky for some parameter k. So in other words, if k equals 1, then we're proposing from exactly pi. If k is bigger than or less than 1, we're proposing from something a little different. But then it's OK, because we accept, reject. It should still work. But how does this work? And let me just show you some graphs to show what happens here. So does it really matter, if k is 1 or k is a little more than 1 or k is a little less than 1? And how's that related to geometric ergodicity? So first of all, if k is 1, then we could call that maybe IID sampling, that is independent and identically distributed, meaning that we're proposing from just the right thing, and that should work great, and that does work great. And here's a graph to try to illustrate that. You probably can't see it here, but here's the exponential e to the minus x function, which is sort of the thing we're trying to converge to. And here's the values that we get as we run this Markov chain. And you can see it's like a really thick head of hair that really shows all the values. And I mean, maybe you can't tell too much from this graph, but actually it's getting exactly the right probabilities, and it's very good. You could look at, for example, the expected value, and we hope the average value is 1. And in this case, I got 1.001. So very, very good. It's working great. So if k is 1, sure, this works great and not too surprising, but what if k is different from 1? It's still a very simple problem. It should work well, but what happens? So let's do the case where k is 0.01, so much smaller. It turns out that in this case, it's still geometrically ergodic. That is, it's easy to see that it's still going to have this exponential convergence to the right answer. And how does it work? So here's again the thing we're trying to converge to, the exponential, and the actual values I get. So if the last one was a nice thick head of hair, this is someone whose hair is thinning, right? It's not working as well, but at the same time, it's not bad. It's getting large values sometimes and small values other times. And actually, this is a pretty good sampler. And if we look at the thing that we hoped on average should be 1, well, it works out in this case to 0.993, so still very, very good. So we can say, okay, fine. If you're using k equals 0.01, it's not as good as when k equals 1 that we had a perfect sampler, but it's fine, right? Which you'd expect. It's such a simple example. It's got to be fine, right? And in that case, it's geometrically ergodic. Let's try one more. What if k is 5? So that is, again, it's still the exponential 1 target, but we're proposing from an exponential 5. Again, then we accept, reject. We know asymptotically it should converge. What could go wrong? Turns out, in this case, it's not hard to show. It's not geometrically ergodic. That is, the convergence of the black bars to the blue bars, or the convergence of the probabilities, is actually not happening exponentially quickly, which is kind of surprising because it's a very simple example. And if you actually graph it, well, here's what I got the first time. So again, here's the target that we're hoping we converge to these probabilities. But in fact, here, these are all really small. You can see as we go up, they're all much smaller than they should be. And if we look at the expected value that it should have been 1, here I got about 0.68. And that's terrible, right? I run this for thousands of iterations, and it's such a simple example, and yet we didn't get the right answer at all. So that's an example of things didn't work well. But you could say, maybe we just got unlucky, right? Because Monte Carlo, obviously it uses randomness or pseudo-randomness to run. Some runs are going to work better than others. Maybe we just got unlucky. Here's another run that's kind of interesting too. So try again. It's another run with k equals 5. Again, we're trying to converge to these probabilities. In this case, it stays small, but then it jumps to a big value and gets stuck there for a really long time. Then it stays small, then it jumps to a big value for a really long time. So this time, the expected value is 1, and I got an estimate that's way too big, 1.69 something. So it's really not working very well. And in fact, I got with Gareth Roberts, who I've done a lot of work on these things with, we got interested in this, and we proved that if k is 5, you'll still, we know asymptotically the black bars converge to the blue bars, but it's going to take over 4 million steps for that to happen. So it's very, very slow. And we found this kind of amazing because it's such a simple example, right? How can anything go wrong? And yet we proved it takes between 4 and 14 million iterations to get close to the right probabilities. Whereas if k is 0.01, even though it had kind of thinning hair, it just takes a few hundred iterations. So this sort of convinced me, geometric ergodicity does make a big difference. And trying to understand how well these things work makes a big difference, because if you're really going to run it in a case where you want to rely on the results of your sample and your simulation and you want to make decisions based on it, depending on what kind of sample you're running, either you're going to get really good answers or you're not going to get good answers. So I want to talk about sort of the question of optimizing MCMC. And I remember the IE department head was telling me that industrial engineering in a nutshell is about optimization. I thought, oh good, one of my slides is about optimizing MCMC. So that's good. So what do I mean by that? I mean that of all possible proposals, which one's best? So if we think of running MCMC, and let's just stick for now to the Metropolis algorithm, where we say, we're going to propose values and then accept or reject them, we have a lot of choice in how we propose them. So remember the way we ran this very simple algorithm. We did plus or minus, each time it proposed to either add 1 or add 2 or subtract 1 or subtract 2, and then it did its proposal. We could do other things too. We could say, what if each time we add 1 or 2 or 3, each with probability of 6, and then we accept or reject? Well, we could run that for a while too, right? So I'll do that a little faster. It's proposing to add 1 or 2 or 3, and then it either accepts or rejects. Last time we just proposed to add 1 or 2 and then accept or reject. Well, Markov chain theory tells us that eventually it's still going to converge. The black bars better converge to the blue bars asymptotically. But again, from a practical point of view, we can't run the chain forever. We want it to converge as quickly as possible, which is better. So, I could run this, faster, and we could say, well, hopefully the black bars converge to the blue bars. But is it better or worse than doing plus or minus just 1 or 2? Or for that matter, if I just do plus or minus 1 each time, right? I could do that too. And so it's doing plus or minus 1 each time. Is that less efficient or more efficient? Now you might think plus or minus 1 is not that efficient because it sort of takes a long time to get, say, from 1 over to 6, and you might be right. But then the other extreme, in fact, let me set up one of my favorite settings, is what's it doing now? Now it's doing plus or minus 1 or 2 or 3 or 4 or 5 or 6 or 7 up to 50. Okay? So it's doing plus or minus, doing these huge proposals each time. Is this working well? Well, not very well, right? Because usually it's proposing things that are so big they're right off the edge of the screen, or in general they're just places where the probabilities get really, really small. So it's going to reject most of them. So you say, well, okay, we don't want to have proposals that are too big because it'll just reject most of them. It'll tend to propose things that are really unlikely. But maybe we don't want proposals that are too small either, because even if it accepts a lot of them, it's not going to move too fast. So, we can say there's a lot of choices, right? They should all asymptotically converge, but how do we know which ones work better or worse? And you could say, well, is there any theory for it? So in this little 6-point example, maybe you could kind of eyeball it or try out a few things and see what seems to be working well. Fair enough. But now you give me a big high-dimensional complicated pie, and I start running my Markov chain, and I hope it's going to converge, and I'm not sure if it's converging that quickly. How do I decide how I can make it better? And it turns out there's some pretty interesting theory. Let me quickly illustrate a little bit. So here's a case where the target was a standard normal, again, for illustrative purposes. And here's a case where the proposal was also normal, but with a standard deviation of 0.1. So just a little proposal. And you can kind of see that here, as we move up, here's time as we move up. And it's wiggling around, and it's accepting most of its moves, but it's not moving very much. And this is kind of like doing just plus or minus 1, where it takes a long time to move. Here's a case where sigma was 25, so it's proposing a really big value. But then it's not working that well either, and you probably can't see too well, but there's long periods of time when these trace plots are just vertical, which corresponds to rejecting a whole bunch of points, right? And it's kind of like the plus or minus 50. It's proposing these big things, and then it's just rejecting them. So this isn't very efficient either. Here's one which is pretty good. It's I took a standard deviation of 2.38. There's actually a reason I chose that. And you can see it's moving around pretty well as it goes. And if we look at, we could say this one, it was too small a proposal. It really isn't moving very much. This one was too big. It was like plus or minus 50. It's getting stuck a lot. This one was just right. If we think in terms of acceptance rate, so one thing that's interesting to monitor while you're running these examples is, remember, it proposes something, and then it accepts or rejects it. Well, it's easy to tell your computer program to keep a count of how many times it accepted and how many times it rejected. And that fraction is the acceptance rate, or the fraction of times it accepted. So here it accepted 96% of the moves. Here it accepted 5% of the moves. And here it accepted about 44% of the moves. And so what can we say? That 96%, you might think that's good. We're not rejecting. We're accepting all these moves. Isn't that great? But it's not so great, because it meant that your proposals were too small, were too timid. So a big acceptance rate is not so good. A small acceptance rate is not good because you're rejecting all the time. You want an in-between acceptance rate. And so you can say, well, that's for this example. Can we say something more general? So we want a moderate acceptance rate. And I sometimes call this the Goldilocks principle, right? So if you remember your Goldilocks story, she wanted porridge that was not too hot, not too cold, but just right. And similarly, when we scale these Markov chains, we want something that proposes not too small, because that's not going to move fast enough, not too big, because that's going to reject all the time, but somewhere in the middle. And we want the acceptance rate to be not too close to 0, because that means we're always rejecting, but not too close to 1, because that means we're not proposing very ambitiously. Something in between as well. And that much you can kind of say just by intuition. But then you say, well, could you say something more concrete about that? And it turns out, in a certain sense, with theory, we can say something much more concrete. And in particular, you could say, well, what is a good acceptance rate? If it should be not too close to 0 and not too close to 1, what should it be? And to spoil the punchline a little bit, it turns out that at least under some strong assumptions, we can actually give an exact decimal form of what the best acceptance rate should be. And that's something I'll talk about. Let's start out by saying, suppose you have a simple random walk, by which I mean something that just adds or subtracts 1 with probability of half each time. And then you do some rescaling, which let me come to the picture. Then it becomes a diffusion. So here's something that each time it adds 1, or subtracts 1, adds 1, subtracts 1 with probability of half each. But then this scary looking rescaling is just saying that instead of doing it once a second, do it d times a second. So you do sort of faster moves. And instead of moving plus or minus 1 each time, just move 1 over the square root of d each time. So you do faster and faster, smaller and smaller moves. Then as d gets large, that converges to Brownian motion, as probably a lot of you know. So this idea that you have a simple thing, just add or subtract 1, but you do it faster and faster, smaller and smaller, and it converges to something really interesting. Well, it turns out that for the Metropolis algorithm, something else holds too, as the dimension goes to infinity. And let me try to quickly say what this is. So this dates back actually to before my time, to Gareth Roberts and his collaborators. And let me skip ahead some of the technicalities. But what it's saying here is that if you take a Metropolis algorithm, look at the first coordinate of it, so it might be a high dimensional thing, speed up time again by a factor of d, so it's doing faster and faster proposals, but then make the proposals smaller and smaller, so it's just proposing a little bit each time, and do this limit in the right way as the dimension goes to infinity. Turns out you get a diffusion limit, which in the limit has a certain speed and a certain acceptance rate. So the speed corresponds to, well, the faster it goes, that's good. That means you're mixing better, you're converging better. The acceptance rate, that's that thing that we can monitor, right? That we know shouldn't be too close to 0 and shouldn't be too close to 1. Well, to optimize this, we should maximize this speed. And so far you could say, well, that's great, but we got this complicated diffusion limit. Now we want to try to maximize its speed, and that's going to give us an optimality result, but it sounds pretty complicated, and it is in a way. But then the amazing thing is, at least in this limit under these conditions, if you compute, you say, okay, once you've adjusted the constants to optimize this diffusion to make it as fast as possible, what acceptance rate do you get? That is, let's look at the acceptance rate at the optimal choice of the parameters. And we said it should be not too close to 0 and not too close to 1. It turns out in their special limit with their special conditions, it works out to 0.234, which is a number, right? And somehow it doesn't depend in some sense on the functional form. So what this is saying is that ideally, if you've scaled your Metropolis algorithm on your big high-dimensional complicated thing correctly, you should scale it so the acceptance rate is not too close to 0 and not too close to 1, and in fact is about 23%, or about a quarter. And that's this sort of amazing result that they have, and that's their optimality. And it's a nice simple rule. It's used in various software that people run for bugs and so on. And it tells you a little more too, that it tells you the optimal proposal shape. So if you're proposing in high dimensions, it's not just a question of how you scale it, but it's a question of like how you propose the different coordinates related to each other. That is the proposal covariance matrix. That's a D by D matrix. And it turns out it's got a certain optimality in terms of the target. And so there's some pretty interesting things here involving these diffusion limit optimality. Now, I want to wrap up soon, so I won't talk about it too much, but what do I want to say? Well, so first of all, some example, I guess I can say this really quickly. Here's an example where the scaling was too small and it didn't work. Here's an example where the scaling was too big and it didn't work. That's not much surprise. Here's an example where the scaling was just right, so the acceptance rate was right, but it still didn't work very well because it didn't have the right shape. And then here's an example where we got the shape of the proposal optimally right too, and it did work. So, so the point is these things are important. I pretty much want to wrap up, but let me just mention something that I won't really have time to talk about, which is adaptive MCMC, which I've been working a lot on lately. And the basic idea, I guess I can say in one word, is that we know this optimality theory, but it depends on things like the acceptance rate and the target covariance that we don't really know. Maybe we could have the computer learn as it goes. And adaptive MCMC is this idea that maybe as the computer goes, it can learn a little more about pi and then use that to run a better Markov chain, and then it can learn more about pi, and then it can run a better Markov chain, and so on. So does that work well in practice? Yes. But on the other hand, does it still converge? This turns out to be subtle because now it's not just a Markov chain. Now we're tweaking based on the whole history and so on. And it turns out sometimes it still converges. But there's a lot of theory for that too, which I'm happy to talk about later, but I don't want to keep people late here. So I'll just say, here's some examples of it working well. But on the other hand, there's various theory under which it's guaranteed to converge, but also I could tweak the applet so that it doesn't converge too when you start adapting. But let me wrap up so I don't take you too long, but I'm happy to talk more afterwards. But just to summarize, let me say that what am I trying to communicate here? Well, if there's only one thing you learn from this talk, I hope you learn that Monte Carlo algorithms, and in particular MCMC, are very widely used in lots of different areas. And as you probably know, they're used a lot in engineering, but they're used in medicine and physics and all sorts of other ways. And they're sort of a way to sample from these complicated distributions pi. And there's also a lot of theory, and that's good. It's kept me in business for the last 20 years, is working on these theoretical questions. And in particular, so one thing you can work on is these quantitative convergence bounds, which I think are really interesting, but they're kind of difficult to do in everyday examples. Then there's these qualitative convergence bounds, like this geometric ergodicity and so on. And it turns out they're important. As I say, I was initially skeptical, but I've come to realize that they provide good guidance for if your algorithm's working well or not. Then there's this optimality I talked about, and sort of this Goldilocks principle that the acceptance rate should be not too big but not too small. and maybe an idealized shape if you know it. But then what I rush, and that can make a big difference in those 20-dimensional examples. But then what I rush through is saying that if you have certain conditions, then it's okay to start adapting the rules as you go. It messes up the Markov chain property. You have to be a lot more careful, but it can provide ways to actually learn as you go and make the algorithms much more efficient in a way that actually converges feasibly instead of not converging. So it can work well, and it still converges under some conditions, which I've been working on a lot. And I think there's a lot more, even though MCMC is used so much, but there's always a lot more scope for new applications, and I'm sure a lot of you are thinking about them or using them, but I think there's all sorts of ways it can be used. And also from the theory point of view, I think there's still, even though we've been working on it a long time, there's a lot more that we don't know than that we do, and there's a lot of interesting questions to try to understand how do these things work, how do we make them work better, how do we optimize them and improve them, and so on. So anyway, I'm happy to talk about it more. If you're interested, all my papers and applets and so on are all on my webpage, probability.ca. And let me just again thank you all so much for your kind hospitality. It's been a real pleasure. Thank you very much.